And what we did not talk about is the second derivative of S with respect to E. We will get to that later. Okay, right? We haven't talked about it yet. So, and one important, and there were mathematical implications. There were mathematical parts of the postulate, like the monotonicity conditions, and we tried to get intuition for all that. But in order to make it helpful, we introduced the first law of thermodynamics, where we said that the change in internal energy of a system can come from the heat given to the system plus the work done on the system. So internal energy change of the system comes from the heat given to the system and the work done on the system. The sign convention is very important. Let's call this equation number 1. And then we said, okay, let's think about the types of work that can be done on a system. So we have some heat given, and Q and W depend on the path that you take. They are not just state dependent, it's the process that characterizes Q and W. So they have the delta sign, they don't have just D. You cannot say Q just on the basis of the state of a system, right? You can say E on the basis of the state of a system. How do we know that the state of a system tells us about E? Any ideas?
Can you rephrase the question?
How do you know that E is a state variable? Go ahead.
Just follow the potentials of the velocity.
No, from postulate, from Callan's postulate in a more rigorous way. How do we know that E is a state variable? Callan's postulate does not say that. Callan's postulate says S is depends on the state, right? But then we have the monotonicity condition, because S depends, S is a state variable, and S of given E and V, you know S, but then we also said that partial E by partial S is monotonic. That's from backside. Okay. So that's why we can write the E. Q, on the other hand, that's an aspect of the process. You cannot say, just because you have a certain system in a certain configuration, that does not say anything about the heat of that system, right? Temperature, and this is when you do undergrad PChem, a lot of students get confused between temperature and heat, right? Heat is an extensive thing that is given to a system. Temperature is a property. It's a characteristic of equilibrium. So we spoke about different types of work. We said, okay, there is one work which we are going to call the pressure volume work, which is given by the external pressure applicable on the system, multiplied by the change in volume of the system. Can you think of other types of work that might exist? Vanessa, what do you think? Can you think of an example? Similar to, your hint is similar to PDV. So pressure and volume is volume, right? I'm giving you more hint. What else can change similar to volume? If you reduce the dimension. Area. dA, right? We could have change in area. So what would be the term next to area? We'll have surface tension, right? Instead of pressure, we will have surface tension. Is that clear to everyone? So we will again have a minus sigma x dA. We could also have some change in length of the system. We could have some line tension. Again, external is always important. As long as, if you're not in equilibrium, you will have an external pressure or external stress or external line tension multiplied by dl, the change in length. What else can we think of? What other form? Is this the only form of work that, yeah, go ahead, Sophia.
So the surface tension and the line tension, I'm just a little confused on how we're staying in the same, I guess, number of, number of dimensions or coordinates, because volume is 3-dimensional, area is 2-dimensional.
Oh, it multiplies out, because pressure and pressure is, what is the unit of pressure? Force over area, right? But sigma does not have the same unit as pressure.
Okay,
Gamma
so
does not have the, it's adjusted in that.
the units are
Yeah. Overall, it's always joule, and everything else exists. So the unit of gamma has to be joule by length. Unit of sigma has to be joule by area. Good. What else? What other form of work can we have in chemistry? Go ahead. Well, there is electric potential, sure, but chemistry, even simpler, or kind of simpler, we can have chemical potential related work, right? When the chemical reaction is happening and you are changing a species A into species B, you will have chemical potential of something, 1 multiplied by the change in number of moles of that thing, dN1. And we can just make it a summation and call it mu I dNi, where I goes from 1 to m in a 1 component system. So this is like all sorts of general forms of work that can happen in a system. In this class, we will concern a lot with pressure volume work, and we will concern a lot with chemical potential based work. We will not be talking so much about, one moment, about sigma and gamma. Yeah, go ahead.
Is it permissible for us to write like PdV and sigma dA sum together? I mean, I can imagine like changing on one system, the same system, changing the volume and something.
Sure. Of course, everything will happen. You can't have a system where volume is changing and area is not changing, right? So most likely there will be some effect like that. But we don't consider it. Most of the time we think about beakers exposed to the atmosphere, and that's our setup that we think about. So this is equation number 2. And as I said, most of the time we will work with the formulation dE is equal to delta Q minus P external dV plus summation over I of mu I dNi. And let's call this 2A. So when I was in grad school, there was a chemistry professor by the name of Bill Goddard, and he was worse than me. He was like more horrible than me. He would go around and be like, you today, now it's your turn. You ask a question. You answer this. You answer this. So you were guaranteed to be asked a question, and it would come at some point. It's quite stressful, but it keeps you awake. Okay, and good. So with this, now we will be using this shortly. I introduced this. Now we will take just a slight step for 2 minutes, and then everything will start to patch in together. So let's get back to our postulate number 2. And there we said we gave intuition for almost all aspects of the second postulate except one. We gave intuition for the monotonicity condition, right? That partial S by partial E is positive. We gave intuition for the other monotonicity condition. We gave intuition for S will increase if you go in non-equilibrium direction. If it's in equilibrium, then S should be the same. One aspect of the second postulate we did not give intuition. Anyone can notice? And someone asked me a question about it. That's your hint. 2 classes ago.
Energy.
No. What about energy? What did we not cover about energy? I'm asking about which part of the second postulate did we not give intuition for? The second postulate said partial S by partial. Second postulate said there exists a state function which depends on NVE such that partial S by partial V, this is 0 positive, this is positive, and S is maximized at equilibrium, blah, 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 right? And there was one more thing. What was it? Go ahead. Related to that, you are in the right direction. It starts with an E. There's one more property of S, which we did not give intuition for. Extensive. We said it's got to be extensive. Why should entropy be extensive? And you have gone along with me, but really think about it. This is abstract function which exists at equilibrium. It's so abstract, right? Entropy. Have you held entropy in hands? I have. No. It's strange. Why should it be extensive? Why should a mathematical function with these properties be extensive, right? We have not yet developed intuition for that, and we will look at that in a moment. Okay, in order to do that, we have to do, so we gave intuition, what is the verb for that? The verb is we intuited all of this. We did not talk about S is extensive, right? And we have to understand. Who asked me about this? You asked me about this, remember? So you should have guessed this. I think you guys need a pop quiz or two to wake up. Everyone seems sleepy. I am the only one who's jet lagged. Why are you all sleepy? Okay. So let's start with thinking about this. So what does it mean to be extensive? In the most rigorous way of thinking about extensive things means that if you have S as a function of E, V, N, and if you multiply everything with lambda, and note all of these things inside the bracket are extensive, right? We are not challenging that. That's how it has been set up. Then an extensive function means that this thing will be equal to lambda of S, E, V, N, right? Same thing applies to energy representation. Energy as, and again, I'm not going to prove that S is extensive. I will give you intuition. I will work through these arguments and you will see why it makes sense to keep it extensive. When you go to StatMech, there will be yet another interpretation from probability theory as to why it should be extensive. Okay, so this is the meaning of something being extensive. So we can also think about intensive functions in thermodynamics, right? We can also, how do we define intensive state functions? What should be the property of intensive state function? If I is some intensive state function, so some intensive state function, that means that I of lambda E, lambda S, not lambda E, lambda S, that's going to be terrible. I of lambda E, lambda V, lambda N should be I of EVN. If you double the size of the system, energy, volume, and number double the thermodynamic limit, but the intensive property stays the same, right? That's the idea. So that's the definition of an intensive function. So what is the simplest way to define intensive functions? The simplest way to do that is to just divide energy by number, right? If energy is extensive, number is extensive, and we talked about this in the very first class. Divide S by number, divide S by volume, divide number by volume. Essentially, you take two extensive things and just take the ratio. I will call this the trivial example. Can we think of a not so trivial, or actually that is also quite easy, not so trivial way of defining intensive functions? Can you think of any? Go ahead. Taking derivative, right? So if E is extensive and N is extensive, then E by N is extensive. But derivative, and now that's where we have to be careful because these are not one variable thing. So I cannot just go and write dE, like we're dE with what, so it's going to be some sort of partial derivative. So let's be careful. So correct. So in order to think about that, not so trivial example of intensive functions come from derivatives. That's terrible handwriting. From derivatives. So what do I mean by that? What I mean is consider E. In the energy representation, what are the natural variables for E? Alex. No, not unit. What goes in the bracket?
Number of particles, chemical potential.
No. You can't put both of them together. It's Alex answering, so no one else. I'm waking him up. Number of particles, what else? Okay, and? Not probably. Stay with confidence. Yes. E of NVS. And this is, I guess, okay, this reminds me, I did not introduce this term to you. These are known as the natural variables of E. What are the natural variables for entropy? I will get to that in a moment. Natural variables are variables when you use a function to write it as a function of those variables, it's thermodynamically complete. Later, we will see that if you were writing E as a function of n, v, and t, you can do that. You will be missing thermodynamic information. It is not complete. So we are getting into that territory where we'll start to think about what does it mean to be thermodynamically complete. And I would have told you about that. Yeah, go ahead.
Can you explain where the lambda goes for the, like at the top equation?
Oh, it just disappears. The point is like, if you have something like temperature, does the temperature depend on whether I have a full cup of coffee or half a cup of coffee? That's the whole idea, right? So you can think of lambda being equal to 2. So the temperature of 2 cups of coffee is equal to temperature of 1 cup of coffee, right? So in this case, lambda was equal to 2. Now you could go to the nanoscale where these things start to break down, but in thermodynamic limit, it doesn't matter. Okay, so natural variables are variables that arise naturally. You know, that's kind of stupid definition, but we will see what they mean in terms of information content. Our Big Bang moment in Chem 684 is that there exists S, which is a function of NVE, right? This says that, Post-Callan says that this is all you need to do in order to characterize equilibrium, right? So if you know S as a function of NVE, you have characterized equilibrium fully, nothing remains. And this is equivalent to writing E as a function of NVS. Okay, and this is a bit abstract. We will keep coming back to natural variables again, and it will become clear. But let's start with our natural variables for E, which is NVS, right? That's how we introduced E. We call this as the energy representation, where E is a function of NVS. So if E is a function of NVS, then what can we say about DE? DE is going to be partial E by partial S, V, and N1, N2. If you have a multiple component system, right? N1, N2, N3, whatever, multiplied by DS plus partial E by partial V, S, N1, N2, multiplied by dV plus partial E by partial N1 multiplied by dN1 V S N2 N3 plus partial E by partial N2 multiplied by dN2 constant V S N1 N3 and there will be many terms like for the number part, right? Corresponding to the species that you have. So these partial derivatives that we introduced here, they are also going to be intensive, right? Because the numerator is extensive, the denominator is extensive. So that's also an intensive variable, all of these. And at this point, the first time you do thermodynamics, you start to cringe a little bit, right? You're like, this is thermodynamics. What does it have to do with chemistry? It's like terrible multivariable calculus, right? Just partial of A with respect to B, keeping Z, M, and Q constant. Like, who's going to remember all this? So let's make our life easy. Let's give these things names, okay? I will write down this equation again on the next page. I call this equation number 3. So we just wrote that dE is equal to partial E by partial S, V, N1, N2 constant multiplied by ds plus partial E by partial V, S, N1, N2 constant multiplied by dV plus summation over I is equal to 1 to M as many components you have, partial E by partial Ni multiplied by dNi S, V, and a bunch of other n's. I will just call it n tilde, okay? We can be mathematically rigorous, but you see my point. You keep every n constant except the one that you are changing. So in order to simplify our life, we are going to call this thing, we will define partial E by partial S at constant V, comma, N. And instead of writing N1, N2, blah, blah, I'm just going to write N. Or actually I can write N1 and 2 ... We will define this as T. also known as the thermodynamic temperature. We have not yet shown as to why this has anything to do with the empirical temperature that you can measure with a thermometer, or your phone tells you whatever the temperature is. But if we could show that this T is indeed the empirical temperature, then just like Sophia pointed out to us, that the temperature of a cup of coffee does not depend on whether you have half a cup of coffee or full cup of coffee, right? Temperature is intensive and energy is extensive. So if temperature is intensive and if energy is extensive, this would imply that S has to be extensive, right? So this is a sort of our intuition. But in order to do that, we have to make sure that this thermodynamic temperature is indeed something we can measure, okay? And we will get to that in a moment. So partial E by partial S at constant V, N1, N2 is our thermodynamic temperature. We call it equation 4a, minus energy, partial energy by partial volume at constant S, N1, N2. What symbol should we give this?
Pressure.
Why?
So at the bottom.
No. Apart from that's good job reading the book. Why?
Because pressure wasn't properly in the previous equation.
Exactly, we have seen that hint. And also, I mean, if you have done any classical mechanics, pressure and volume are conjugate variables, right? In different formulations of mechanics. But we will call it our thermodynamic pressure. Okay, P. Let's call this equation 4b. And notice we have a minus sign over here. Partial E by partial N1 at constant S, V, N2, N3, dot, dot, dot. We are going to call mu1. And this becomes equation 4c. So this is thermodynamic temperature. This is thermodynamic pressure. And this one is chemical potential. I'm not going to use thermodynamic all the time because in a moment I'm going to show you that it is consistent with the empirical temperature and the empirical pressure. We don't have to keep using two definitions of we don't have to go like empirical swim in and thermodynamic swim in. You know, it's all the same. Okay, good. So sometimes this temperature is also called conjugate variable to S. So you can see in the energy representation, temperature is accompanied by change in S. So if we write down let me first write down equation 3. This is equation 3 by using this notation that we have just introduced. So, and then I will get to the conjugate variable part. Okay, let me scratch what I said about conjugate variable. Let me write down equation 3 again, then I will get to it. If you wrote it, you don't need to erase it, it's fine. So therefore, dE is going to look like TdS minus PdV plus summation I is equal to 1 to M mu I dNi. Huh?
In this corner as a suggestion, maybe use Einstein notation for this sum.
I hear your suggestion. I sympathize with you, but I overrule it. I know what you mean. The Einstein notation. Do you have a physics background? Do your friends in the corner have physics backgrounds?
Yes.
Yeah. So you love the Einstein notation. The chemists are gonna hate me. Okay. So let's stick with a notation which has more information. Einstein notation is simpler. Sorry. If that said, if in your exam you write it in Einstein notation means you can ignore the summation and life is simpler. I will not deduct your points. Okay, so you can do that, but I'm gonna be explicit. This equation is the single most important equation in thermodynamics. It is known as the integrated first and second law. Is there anyone here who likes organic chemistry? You like it? Cool. So if you were stuck on an island and you could have only one chemical to start with, which chemical would you have?
Water, I mean,
Water is there, an island, and maybe, okay, let's say the salinity, you have solved this salinity problem. You can drink seawater, let's say that. Okay, water is there. After, good point, water is important. You're full of wisdom today. Apart from water, what else would you like?
do I have any chance of escaping?
No.
Okay, that's cyanide.
No. You have to stay there. You would probably want alcohol, ethyl alcohol, right? If you get really bored, you can have something. And so the reason I say this because there's a book on organic chemistry, which is known as Morrison Boyd. Maybe some of you know it. It's very popular in India, or at least used to be. The chapter on alcohol, he starts by saying this. You know, there is this English book, Robinson Crusoe by Daniel Defoe, where Crusoe gets stuck on an island and he has to do everything. You have read it? You're nodding your head. Rob. Long time, but you remember the book, right? He gets stuck on an island. So the book starts by saying that the chapter on or alcohol starts by saying that imagine you are a chemical Crusoe, you're stuck on an island. So the one chemical you would like is C2H5OH, because by mixing it with sand, with water, you can create basically everything that you want. You can start from there. So this equation is like our ethyl alcohol. Okay, that's the long story. It's super important. From this, you can derive absolutely everything. Why is it so important? In order to get here, we used the second law of thermodynamics, right? We used our Callan's postulate. We started, none of this would have happened if we did not know that S of n comma V comma E exists, right? From there, we use the energy representation. On top of that, it also has information about first law. The first law actually falls out of it. You will see now, okay? So how does it connect with first law? Before doing that, I'm going to make my point about the conjugate variable. So now you can see that T is conjugate variable to S. P is conjugate to V, and technically minus P is conjugate, but you know, E is still, and mu I is conjugate to Ni. Okay, so they come in pairs. It's very rare that you will see TDN or PDS. You know, you will typically see TDS, and that also goes back to when I think it was Sophia who asked about the units earlier on, right? These things, when they multiply, they give you units of energy. That's one of them. Yeah, go ahead. Two. Yeah, you first.
That doesn't mean that.
No, she first. She goes first.
Okay, I probably won't be answering through Alex's question, but so you can directly calculate when you're running simulations, entropy, energy, things like that easily, but then when you're doing experimental work, you can only directly measure the conjugate variables,
Yeah.
which leaves you with the derivatives, the partial
Yeah,
derivatives.
yeah.
So are you still missing thermodynamics?
Oh, we will talk so much about it. We'll talk so much. But also, I want to point out one thing. Why did you say in simulations you can measure energy and entropy?
I ran MD simulations.
Entropy is actually very hard. So this is a special problem for you, okay? I want you to go and think about it. If you have time, and tell me, can you get entropy out of an MD simulation directly? Energy is very easy. Your force field just puts it. Entropy, you have to run it at 2 temperatures and then differentiate in order to get it. Okay, good question. Yeah, Alex.
Does it mean that our T space and S space are null spaces from the German transformation definition? Which we
Yeah. We will study so much about that. That's why I introduced Alexander transform, because it's key to this subject. So we have D is equal to TDS minus PDV plus mu I dni. Let's call it equation number 5. But we have seen DE and minus PDV in some other form also before, right? We saw it in the context of first law of thermodynamics. So let me write down equation 5 once again, so we will compare it. So DE is equal to TDS minus PDV. I'm sure I'm louder than him. Hello? Mu I dni, okay? So this is equation number 5 for some m component system. We have also seen dE is equal to delta Q minus P external dV plus summation I is equal to 1 to n mu I dni. So it's very tempting to compare these two equations, right? They look so similar. And if you compare them, then we would get a connection between heat and entropy, and that would be fantastic. There is one problem. The bottom equation has P external, the top one has P. And in fact, you could apply the same thing about chemical potential also if you were not being so sloppy, okay? So if we were changing things reversibly, then above equation, and what is above equation? We have seen it earlier. We numbered it. This was equation number 2a. So this was equation 2a. Then above equation 2a becomes dE is equal to delta Q reversible. And even though it's reversible change, we still have to use the squiggly delta, right? Because different paths, even if they are reversible, they will still have delta. They will have path dependence minus P dV. The external goes away. This is now the pressure of the system. Plus mu I dni. So if now I compare these two, what do I get? I get TdS is equal to delta Q reversible. I'm going to write it the other way. Delta Q reversible is equal to TdS. That is the first time that we have expressed the change in entropy as something which we could perhaps measure with an instrument, right? If we, one moment. If we are taking a system from one state A to some state B, and if we are doing it reversibly, then the entropy difference between state B minus state A can be calculated by delta Q reversible divided by T going from A to B. And why is this equation so fascinating? I will call it equation number 6. Let's say you did it along path 1, this path, okay, path 1. Now let's say I have another path that goes from A to B along this direction, and I call it path 2. This is also reversible, okay? And anytime I draw things, I should specify what my coordinates are. Let's say this is pressure, volume, some properties, okay? If I was to calculate AB delta Q reversible by temperature along path 2, would it be the same or different?
Staying the same.
Why?
Because entropy is a state.
Because entropy is a state function. That's kind of amazing, right? Doesn't matter which path you take, you can do whatever you want to your system. So I mean, I could take Omar and take him to the next room upstairs and come back, and then I don't know, just hit him through the wall and take him to the next room. The heat will be definitely very, very different, right? But the entropy change will be the same, as long as I do both processes reversibly. If it's irreversible, then there is a problem. Yeah, go ahead.
Didn't we define a reversible process as a process where entropy doesn't change?
That's a good contradiction. How do we solve this? Any idea?
I have a guess.
Yeah.
Like it's reversible on, and if it doesn't it's like each step is reversible as in, like with your process very slowly doesn't mean it's reversible overall. It's like it's at equilibrium at each step.
Yeah. Yeah. But that's a very good point. So what Omar is talking about is when we talked about, and I will remind myself that Omar brought this up, so I will draw his face.
I'm not that big.
Don't worry.
Yeah, that is fair.
You have glasses? Yeah, you have glasses. You have to be accurate.
He's like white teeth.
Okay. So Omar said that when we were talking about which coordinates did we think about when we were doing the piston paddle thing, we had energy and volume, right? And we were talking about this. Yeah. So we said that entropy is maximized at equilibrium, right? But maximized means that it's for small changes. So when you make a small change, it's not going to change. Otherwise, entropy does depend on the state. That's where we started with, right? I mean, that's what Callan said, that ENV gives you the value of the S. But the point is that if you are in equilibrium and you make a slight perturbation in value of E and V, entropy will not just shoot up. It will stay where it is. It is maximum, right? Which is, and this will become clear when we go to the Legendre transforms. And I really, if you want to get intuition into it, go already to the chapter in Callan on Legendre transforms, and he has nice surfaces where he shows what this means. You stay on this surface. Okay.
Can we use the word quasi-static here?
Yeah. Quasi-static is same. I mean, I will use it interchangeably, even though there can be arguments made over that. So the recap here was that S is maximized at equilibrium, but state A and state B in general, SA might not be equal to SB if you're doing an adiabatic process. So the other reason why we had that example over there is because we were thinking only about piston work, which was done adiabatically, right? So in general, it won't be an adiabatic process and S will change as you go from A to B. Yeah, but that's a good point. So let's go back to equation 6. Yeah.
So you just said that chemical potential also depends for universal. So when you go from equation 2 to equation the next line,
Yeah.
so a chemical potential is also something like external.
Yeah. So if I was to be very, very technical, I would write it as mu I external.
So what does it mean? Mu I external and mu normal mu I?
It means, for example, you have a battery and you have a membrane, and on the right side of the membrane, it really wants to have a lot of oxygen. On the left side of the membrane, on the right side of the membrane, you have a lot of oxygen. On the left side of the membrane, you have very little oxygen, but you're forcing it to stay that way. And when you make holes in the membrane, they will come to equilibrium. Chemical potential sounds abstract, but it is just like temperature. It's not really different. Okay, it takes time to become comfortable with it. First of all, it got a funky Greek symbol.
Difference between an external chemical potential and
All it means is chemical potential of the surroundings is different from the chemical potential of the system. That's the only thing. Okay, just like temperature of the surrounding is different from temperature of the system. That's the whole idea. Okay, so we just showed that delta Q reversible is equal to TdS, which allows us a way to calculate the change in entropy. And again, going back to the piston thing, I mean, actually our life is very simple, because what happens to this one in the piston example?
Sorry?
In the piston example, what happens to delta Q reversible? Zero. That's why SB is equal to SA even along longer paths, right? If it's a fully adiabatic process, it really stays constant. So that's actually truest answer to your contradiction.
So that external is always
Slow is always there because we are talking about delta Q reversible. If we were not talking about slow processes, then later we will study something known as Clausius inequality, and this thing becomes an inequality. Go ahead.
So I still don't understand. So he asked the question about the reversible processes
Yeah.
and entropy changing. I still don't understand your explanation. I thought reversible process is one where entropy doesn't change. Or is that just,
An adiabatic reversible process. Adiabatic is important.
so, okay.
Yeah,
So
okay.
that's the,
Adiabatic process is where Q is equal to 0. Okay, so let's be careful in that. Let me write it down. And I can see where the confusion came from. So, and now it's better to write this because we have introduced this equation. So equation 6 said delta Q reversible is equal to TdS. Okay. Adiabatic process. What is the definition of an adiabatic process? When we talked about adiabatic boundary, it was when no heat is being exchanged, right? So adiabatic process is delta Q is equal to 0. Note, adiabatic process on its own can be reversible or irreversible, right? You could do a process in a reversible container or in a conversible. So adiabatic reversible process has delta Q reversible equal to 0. Therefore, ds is equal to 0 for adiabatic reversible process. Okay. Still confused or clear? Good. No, I'm very glad that you are asking questions. Otherwise, this stuff is like at the end of the semester, like what was that? Right.
so on the previous slide, how did we, I think I missed how we resolved the issue with the difference between the empirical and the P and P external. You mentioned,
Oh, we said, no. Are you talking about empirical pressure versus thermodynamic pressure?
right,
Okay, no, we haven't resolved it yet.
okay,
I'm going to resolve it for temperature, and you are going to resolve it for pressure and chemical potential in second homework, which will be out this weekend. Giving out homeworks is way more fun than doing it. And grading them is not that much fun. Okay. So now I am going to draw Patrick. He does not have glasses. He has a big grin. And he has approximately yellow hair. Okay. You might say that I'm getting distracted, but if I did not do things like this every once in a while, I would cover way more syllables than you want to. Okay. So it's in your interest. Trust me. Okay. So now let's develop intuition as to why partial E by partial S at constant n comma v is related to the temperature that we can measure in an instrument, related, which we know as the empirical temperature. Okay. What does it have to do with the temperature that you measure on an instrument? Why is it okay that after this class you can go and tell someone, oh, the partial E by partial S seems very high today? You know, you can do that and it's completely correct. This is the most accurate definition of temperature. In order to do that, and same thing applies for pressure and chemical potential, and it will be on your next homework. Okay, so you can just go and solve it, and one problem on your homework is done. And it's the same idea as I'm going to show it for temperature. So let's consider a system with, so it's a two-part system, and we have some sort of boundary in the middle. And it's all insulated from the outside. So this hatched line in thermodynamics means it's perfectly insulated. It's as a whole, it's adiabatic. No heat is going in and out. So we are going to consider a closed composite system with different thermodynamic temperatures on side 1 and side 2. Okay, so let's call our thermodynamic temperature with this symbol. Let's reserve this special symbol for it, okay, for now. Or is it going to confuse things when you look at your notes later? Yeah, it will confuse things. Yeah, forget about that. No, the special symbol. So we are talking about T, which is partial S by partial E at constant Vn, and there is only one T, okay, because it will become the empirical temperature. So let's not use a special T. It is the thermodynamic temperature. And what we are saying is that on the left side, you have T1, and on the right side, you have T2. There are two different values of this partial derivative on both sides, and they are separated by this internal constraint in the middle that is not allowing anything to happen. And let's assume that T1 is more than T2. Okay, that the partial derivative, one moment, that the partial derivative partial E by partial S on side 1 is more than partial derivative E by S on side 2. Yeah, go ahead.
The partial should be ds, right?
Oh, you are paying attention. Yeah, you're right. Absolutely correct. So now let's remove the constraint. If this T was indeed the empirical temperature and you remove the constraint, then what should happen? What's your name? Can you remind me? Johan? Johan Pang. Okay, I'll get that. Can you, so yeah, since you, I don't want to lose you from the class, so tell me, if temperature, we have talked about all this thermodynamic temperature business, right? But let's say if this was the actual temperature that you can measure with a thermometer, and you have a box where one side of the box is very hot and the other side of the box is very cold, and you have a boundary in the middle, so this one stays hot, this one stays cold. This one hot, this one cold. Now I remove the boundary. What do you think will happen? From hot to cold, right? So in this setup, if I can show that the effect of removing the boundary is that the same thing happens, that energy flows from side 1 to side 2, that means that, maybe this is like the temperature that we know, right? That's the idea of what we are going to do, okay? That if the partial derivative of E with respect to S is higher on side 1 and lower on side 2, and we remove the boundary, and then suddenly energy goes from side 1 to side 2, that means indeed this thermodynamic temperature behaves like the empirical temperature, right? Because that's the most important thing we know about empirical temperature, right? It tells us the direction of heat flow, the direction of energy flow, and then we got to be careful with whether heat is moving or energy is moving. So let's look at that carefully. So, but first of all, when we remove the constraint, what will happen to delta S, which we define as the delta S coming from delta S of system 1 plus delta S of system 2? Can we say anything about delta S in this process? Will it be 0? Will it be negative? Will it be positive? Why?
Because the system is mission of equilibrium. I mean, we know that the system will change anyway.
We introduced this setup in the postulate itself. We said removing of internal constraints leads to entropy getting higher, right? This is abstract. If you feel lost at this point, it's totally okay. Send me a message and I'll try to explain more, okay, through some other material on Slack or whatever. So send me a message. This is abstract. It's why this internal constraint business happens. It confuses, I get confused like every other month. And then I have to remind myself as to why it works. So removing internal constraints leads to entropy getting higher. And it's not just about temperature, it's the idea of that, let's say if all the women in this class were sitting on the left side, all the guys in the class were sitting on the right side on the internal constraint, and I remove it, all of a sudden we'll start moving around, and you are not all of a sudden automatically going to form a configuration that all the women are on one side and all the men are on the other side, right? You will stay in that mixed configuration, right? So Now let's think about the change in energy of system 1 plus change in energy of system 2. What can we say about this one? Someone who hasn't answered. JP has answered. Who hasn't answered? I'm sorry, what's your name? Yeah, you. Michaela, sorry. Michaela Grainer? Grainer. Michaela, what will happen to this one? Delta E1 plus delta E2. And I promise I won't go around asking you questions by your name. This is just to make sure that you have all actually asked, so I think it helps you next time to, interrupt me. If I have interrupted you once, you're like, oh, now I gotta take revenge. What can we say about this one? Can we say this will be positive, negative, 0? It will be 0 because the whole thing is insulated, right? The whole thing is insulated. Where is the energy going to go? Entropy is funky. You can create it at will, right? It can, entropy can do funky things. Energy is conserved. It's not going to go up. Why? You have a problem?
Yes.
Go ahead.
But don't fly through the universe redshift due to universe inflation, where the energy does go.
This is my universe. It stays in the universe. It's not going outside the universe. You're really asking something to happen outside the universe. This is my universe. Yeah. Oh, and I forgot, this is Patrick. Patrick K. So this is 0. Does everyone agree? Michaela, do you agree with her? Do you buy that? Okay. Because something happened to the energy in 1, something happened to the energy in 2. We don't quite know yet whether delta E1 is positive or negative. If you knew, then, well, there is nothing to prove, right? That's what we are trying to prove. We are trying to prove, what are we trying to prove? We are trying to prove is that if T1 is more than T2, then delta E1 should be negative, right? The energy for 1 should have gone down and go to the right side. That's what we are trying to prove, right? So, but we do know that it's conservation of energy, right? If it decreased in 1, it has to increase in 2. If it increased in 2, it has to decrease in 1. That's what we said here. So let's call this as equation 7. Okay. Now I'm going to turn the page. So for small changes, which is really what we do in thermodynamics, lots and lots of small changes, very, very slowly. For small changes, we can write delta S as partial. So for any change, delta S is delta S1 plus delta S2, right? This is true for any change, small change, large change. But for small change, we can write it as approximately partial S1 by partial E1 at volume of V1 multiplied by delta E1 plus partial S2 by partial E2 at volume 2 constant multiplied by delta E2. Why is the volume and the number is also constant? Because when we remove this internal constraint, we allowed energy to pass, okay? We did not allow the mass to exchange. We did not allow volume to exchange. Why are you allowed to do that? Because we are talking about temperature. In your homework, you will be doing an analogous thing where you will move your constraint in a different way. You will allow mass to happen, and that's how you will prove the idea for pressure. So it should be, that will make sure that you get this concept correct. So we just showed that this thing should be more than equal to 0 as per equation 7, right? We said that delta S should be positive. That's really Callan's postulate. So do we have a better way of writing down this thing? That's the thermodynamic temperature, right? Or, well, the same mistake as I did last time. It's 1 over the thermodynamic temperature, right? So it's going to be 1 by T1. And suddenly my numbers became Roman numeral. So here I was using Arabic and it became Roman, sorry. I can also write in Hindi. Do I know how to write in Hindi? Numbers? No, I've forgotten. It's terrible. So, what? That was a comment. What was the comment?
No, I know because we use the narrative.
Oh, yeah. So this means that 1 by T1, this is 1 by T1 multiplied by delta I. Okay, I can't really mix in the same equation. Let's call it delta I1 plus 1 by T2 delta E2 is positive. But we also know that delta E1 plus delta E2 is equal to 0, right? So delta E2 is equal to minus delta E1. Or 1 by T1 delta E1 minus 1 by T2 delta E1 is positive. Or 1 by T1 minus 1 by T2 multiplied by delta E1 is positive. How did we set up our problem? We said initially that T1 is more than T2, right? That's how we started, right? Just one moment. Yeah, go ahead.
I'm not quite sure why we said that the partial as a partial is 1 with T. I mean, this is not a total derivative, right? So why are we?
That's a very good point. You guys are keeping me on my feet.
So this is the definition.
This is the definition.
Oh,
It's actually 1 over T, which is defined. And if any of you, huh?
in the first equation, then you can replace partial by T again. Okay.
Yeah, this equation won't change. So let's go back to this one. So, but it's also a well-behaved derivative. So I think there is no problem in switching the order.
But you have to use the chain rule. I mean, it's not.
You have to use chain rule in order to calculate it, which is another story, but you can write it. So the point I'm making here is that T is going to be partial E by partial S. No, let me be careful. Let me be careful. Let me be careful.
Is that would be the partial B like 0?
No. This is actually a very good point. Sorry. I was correct in writing what I did over here. This does define temperature. This is a very excellent point. We could have defined temperature in another way. Instead of using the energy representation, we could have used the entropy representation. Instead of thinking about dE, we could have thought about ds. And then we would have partial S by partial E. Right? And that thing would be 1 over temperature.
So if you're moving from conjugate variables, you're just flip the.
Yeah. You see, so all of this, we could have written a similar thing where we would have ds is equal to 1 by T dE plus T by T dV and some term for the chemical potential. And actually, there remains a bit of work to prove that the thermodynamic temperature here is the same as the thermodynamic temperature earlier. That's where the missing part of the story comes from. Okay, but for now, let's be sloppy mathematicians and let's not worry too much about inverting it, but it's really comes from. I will clarify it in notes later. Yeah, but that's a good point. So we know that temperature 1 is more than temperature 2. Okay. Let's see if I can be less sloppy about this. I mean, at this point, we don't have to be sloppy because we could just have said, yeah, I mean, why are we sloppy? Let's be more rigorous. I will erase this and say, this is equal to Better? That's correct. There is no approximation here. So I wasn't sloppy. I can sleep better. This is more than 0. And now we know we are purely consistent. We saw in equation number 4 that this thing in the denominator is the temperature. Just one moment, Sophia. So equation 4, using 4, we get delta E1 by T1 plus delta E2 by T2 is more than 0, but delta E1 is equal to minus delta E2 per equation 7. Yeah, I haven't forgotten you, Sophia, just one moment. So therefore, 1 by T1 minus 1 by T2 delta E1 is positive. Yeah, go ahead, Sophia, you had a question.
So how do you get from delta S1 over delta E2?
Oh, that's that's just multivariable calculus, right? This thing is equal to this thing. F as a function of x, y, z, right? So I'm comparing partial f by partial x at yz to 1 over partial x by partial f at yz.
I have a question. On the other slide, you were talking about how we didn't know if delta E1 or delta E2, like the signs of them, because they'll both equal 0. So how can you say that?
Oh, I don't know their sign, but am I making any claim about which one is positive?
No, but you.
No, I'm not. I'm saying we have a total sum of money. Either it went from you to me or me to you, but nowhere else. So I haven't said anything here about which one is positive. Not yet. That's what I'm going to prove now. Do you agree with this statement?
Yeah, but I'm more concerned about the next statement.
Oh, I haven't said anything. I haven't said anything. Next statement. Okay, let me write down. Okay, let's stay with you. I don't want any lingering concerns. Do you agree with this statement? Do you do? That is just delta S being positive. Okay, so let's take this statement. Remind me of name again? Nick. So Nick agrees with that one. And then this one, I'm going to say delta E1 by T1. And Nick also agrees with this statement, right? Nick said he agrees with this. So I can say plus minus delta E1 by T2 more than 0. That's all I had written. Or 1 over T1 minus 1 over T2 multiplied by delta E1 more than 0. So I had skipped a line in the middle, but that's what we had. Okay. So now, and we are about to finish today's class, we had said that T1 is more than T2, right? Therefore, 1 over T1 is less than 1 over T2. Can we really say that? If A is more than B, is 1 by A always less than 1 by B? Sign has got to be the same. And do we know something about the sign here yet? We do. It's the monotonicity condition. The sign is positive. We are saved. If we didn't have the monotonicity, if we did not know that partial S by partial E is positive, then we would not be able to do this. So the only reason we can do this because we know together, both of them are more than 0. That's the only reason. Otherwise, this wouldn't happen. Therefore, 1 by T1 minus 1 by T2 is negative. So if we just showed that this thing is negative, negative multiplied by something positive, what does that mean? Delta E1 is negative, right? Therefore, delta E1 is negative. Therefore, energy did go from left to right. Energy flows in the direction of thermodynamically high temperature to thermodynamically low temperature. Therefore, it's okay to call thermodynamic temperature as the empirical temperature, making Patrick's grin bigger. Hopefully. Are you happy, Patrick?
I guess so.
Good. What do you mean, guess so?
It's the best I can do.
Okay. Yes. Yeah, no comments. So let me summarize this. Therefore, energy flows from high thermodynamic temperature to low thermodynamic temperature, which is the same behavior as empirical temperature. As empirical temperature, something we can measure with a thermometer. Therefore, T is equal to partial E by partial S at constant NV is indeed the temperature. And this immediately has a profound conclusion that the temperature must be positive. Now, at this point, Alex would say normally, but Alex already said it in the first class, that no, I know about negative temperature systems. Negative temperature systems exist. And guess what? Negative temperature is actually hotter than absolute zero, which is the funkiest thing. But negative temperatures have been realized in lab, but they happen in systems with finite number of particles. Thermodynamics is true only in the limit of n tends to infinity. If you go to a system where you have finite, so in quantum systems where you're really controlling the number of layers, you can have negative temperature, and that's another story. So I'm going to stop here. Next time we will talk about equations of state, and that goes to, who is it? What's your name behind Michaela? Let me see it. No, what's your name? Huh? Aurelia. Yes, Aurelia. Aurelia's question as to how do you go from partial derivative. What was your question? Yeah, so she said that I can measure temperature, which is the partial derivative of entropy or energy, right? So how do I go from something which is a derivative to the actual thing? So next time we will start talking about